complete theory of conditional expectations is a fairly deep topic. Okay. What we will do is we will develop a somewhat elementary version of conditional expectations for discrete random variables and for jointly continuous random variables. Okay. So, for both discrete case and the jointly continuous case, we have respectively the conditional PMFs and the conditional PDFs, right. So, we will just define the conditional expectation as the expectation taken with respect to the conditional PMF for the conditional PDF. So, that is a very elementary way of developing the topic. However, if you do not have, so the conditional expectation is a concept that is defined actually in more full generality, okay. But developing that will require some more tools from measure theory and some more properties of L2 spaces and so on. It is a little bit beyond the scope of it is a little bit too advanced for us for our purposes. Okay. So, I will develop it somewhat in an elementary fashion for discrete random variables and jointly continuous random variables, and then just hint at what it takes to generalize it. Okay. Yeah, but you do not have to worry about the most general treatment. Okay. So, conditional expectation. So, let us take, so to start with, let us take, let x and y be discrete random variables with joint PMF. So, if x and y are discrete, the joint PMF says everything I need to know about x and y. So, let us say p x y of x comma y is given. Okay. Recall the conditional PMF was defined as follows. P x given y of little x given little y is equal to P x comma y of x comma y over P y of y, right, assuming that this is non-zero. This should be strictly positive, the denominator should be strictly positive. Right. So, you are fixing capital Y equal to little y and you are looking at the distribution of x given y equal to y. If you recall that picture, you have some, right, you have some discrete probability masses sitting on R2, you are saying that I am going to fix y equal to y, right, and you are saying you are looking at, you are just scaling the joint law by p y of y, this is say y equal to y little y, and then you are looking at the distribution of x in this y, right, that is the interpretation. Now, what we are going to do is conditional expectation of x given y equal to y will simply be the expectation taken with respect to this conditional PMF. Okay. Define expectation of x given y equal to little y as sum over all the relevant x's x p x given y of x given little y. Okay. So, this will be a number which depends on the value of little y, right. So, if you fix this little y, you get some answer, right. If you fix some other little y, you will get some other answer. Okay. So, you can think of this guy, this summation here as some function of little y. Okay. So, let me just call it, so I can just say, so I can call this psi of little y, right. So, this will be some function of little y, you agree with that, right. I am just going to call that psi of little y. So, if you have this little y, you will get some value, if you have some other little y, you will get some other value. Okay. So, in the discrete case, so now I am going to do the following. The random variable psi of big Y is called the conditional expectation of x given y, and is denoted E x given capital Y. So, this is the key step. Okay. So, this is not called the conditional expectation, this is the conditional expectation of x given y equal to little y. Okay. But of course, this object here changes whenever little y changes, depending on the value of capital Y, whatever value it takes, you get different values for this guy here. I am calling that psi of little y. Okay. Now, this little y itself is a value taken by the random variable capital Y. Okay. So, I am considering the random variable psi of capital Y. Understand what I mean? So, the psi of capital Y is a random variable. Okay, this is just a number for little y equal to little y, this is just a number, that is not the conditional expectation, that is the conditional expectation of x given y equals little y. But when I replace, so this will be some function of y, right, this may be, you can explicitly calculate it to be some function of y, just replace small y with capital Y, then you get some random variable, right, that is called the conditional expectation of x given y. Okay. It is a random variable, and it is a random variable that depends only on y, correct, in this definition. So, this is only for discrete, by the way, right. So, to say it a little more precisely, so you know, see, you can think of this as some function, some psi of capital Y, right. So, y is some random variable, I am looking at some function psi of capital Y, which has a very specific definition, but you know that any function of y will be a random variable which is measurable under the sigma algebra generated by y, right. So, this guy will be a random variable, not just measurable under f, the bigger sigma algebra, but it is actually measurable under sigma y, right. That is, I think that is something you proved in your homework or your exam, I guess, right. So, any function if you have x, f of x is measurable under sigma of x, right. So, this you can think of as a random variable, and it is a random variable measurable under sigma y. Similarly, you can define expectation of y given x. Okay, you will take the PMF the other way, you define expectation of y equal to y given x is equal to little x, it will be some function of little x, replace x with capital X. Okay, that is called the conditional expectation of y given x. Okay, and this is the notation for it. Okay. So, this is what, this is a random variable, this is not, so do not be fooled by the expectation here. Normally, when you have expectation of something, you get a number, right, but if you do that, you get a random variable which is only a function of what is on the right side of this vertical stick. Okay. So, essentially you can think of it as averaging x out, but what remains is some function of the random variable, that is some function of what is on this side of the line. Okay. With me? So, example, actually let me just do it for I might as well just give the, I will give an example after defining it for jointly continuous case as well. Okay. So, let x and y be jointly continuous with joint PDF probability density function f x comma y of x comma y. recall the conditional PDF recall the conditional PDF f x given y of x given little y. It was defined as what? The joint over marginal of y, and it is defined whenever the denominator is strictly positive, right. This was the definition of the conditional PDF. Okay. So, now define. So, I am just going to define my conditional expectation of x given y equal to y as the expectation with respect to this joint with respect to this conditional PDF. Okay. So, I am just going to say define expectation of x given y equal to little y as the integral over x f x y. So, f x given y d lambda, right, dx if you like, all right. So, I am taking this conditional density and integrating calculating expectation with respect to that conditional density, okay, and that is what I am going to call the conditional expectation of x given y equal to y little y, okay. But this is not the conditional expectation again, okay. So, I am this will be from function of little y as usual, right. So, I am integrating x out. So, what remains will be some function of little y, okay. So, whatever function of little y you get, you replace blindly little y with capital Y, okay. So, you call that now psi little y. I am using the same symbol, so that I mean this psi and this same may actually may not be the same, but I am using the same notation, okay. So, this psi y is again the psi y is, so the random variable psi y is called the conditional expectation. Of same denoted the same thing. So, the random variable so is that clear. So far, so if you are either given discrete random variables or jointly continuous random variables, you go ahead and find either the conditional PMF or the conditional PDF, calculate the expectation with respect to that, you will get what you will get is the function of the variable you are conditioning on, right. So, replace that little y or little x with big Y or big X, and you call that random variable the conditional expectation, okay. So, expectation is always a number, conditional expectation is always a random variable, okay. It is always a random variable, and furthermore it is a random variable measurable with respect to the variable you are conditioning sigma of y in this case, right, the sigma algebra generated by the variable you are conditioning on, okay. So, this viewpoint is good to keep in mind, because the general definition of conditional expectation is in terms of these the existence of a random variable which is sigma x sigma y measurable, okay. So, for now this is okay, alright. So, just for the discrete case and the continuous case, jointly continuous case, we are okay. So, if you notice, I mean very little of what I did was so far very specific to discrete random variables or continuous random variables, right. We have developed till expectations, we developed in full generality, right. This I am not developing in full generality, because it requires a little more mathematical tools, okay. So far okay. So, what we will do is we will discuss some properties of the conditional expectation that we have so far defined for these two special cases. Okay. Some of these key properties will actually help us understand how the conditional expectation is defined in a very general case, where x and y may not be, they may be singular mixtures, what have you, right. Okay, so let us look at some properties. See, the first property is a very important one. So, I have defined, okay, so let me just give you an example before going on to properties. Okay. So, let us just so that you know what exactly I am talking about. So, let us have let f. So, I will give you an example for the jointly continuous case. F x y is equal to 1 over x for 0 less than y less than or equal to x less than or equal to 1. Find expectation of y given x. Okay, this is the problem. I am giving you some joint. Okay, I am asking you to find expectation of y given x. Okay, and this will be a random variable. It is a function of random variable that depends on capital X. Okay. So, let us see what this density looks like. So, that is my y, that is my x. So, first of all, where is this range, right? This is x is between 0 and 1 and x is greater than or equal to y, is not it, which means I have to be 0 less than y. So, which means I should be here, is not it, is that right? This is correct, right. So, in this range I have a value 1 over x for this f x y, right. So, you can verify. So, if you want to verify this is a density, you will integrate y from 0 to x, right, and integrate x from 0 to 1, correct, and then you will see this is a valid PDF. Okay. It is not uniform here, it is 1 over x in this range. Okay. Okay, good. So, what do I have to do now? I have to find, so first of all I need the marginal, right. I have to compute this guy conditional density, which means I need the marginal density of y. So, let us find the marginal density of y. So, f y of, well, actually I need the marginal density of x, is it not? So, f I need f x or f x of x, which means I have to integrate y out, right. So, that will be y will go from 0 to x, right. So, integral y going from 0 to x dy over x, right. So, that is equal to what? 1. Fine. Great. So, which means that x itself is, so this is for x is in, so 0 less than x less than or equal to 1, right. So, this is a uniform, x is uniform, is not it? Did I make any mistake? No, right. Okay. So, okay, great. So, now I have to find the conditional of x given a conditional density of x given y. So, f x given y of little x given little y is equal to f x y over, well, the other way around, is not it? I have to do y given x, no, over f x of x. Okay. So, which is equal to one over x for 0 less than y less than or equal to x, which means y is uniform in 0 to x, correct with me, great. So, if I want to find so if I want to find expectation of y given x is equal to little x, that will be equal to integral so I have to integrate this guy with respect to, so y times 1 over x, I have to integrate with respect to y, and y goes from 0 to x, correct. So, and this will be equal to x squared over 2, that is equal to x over 2, correct. Let us integrate this out. Therefore, what is the conditional expectation now? So, the conditional expectation, this is not the conditional expectation, right, this is, so I want to have conditional expectation of big Y given big X, right, that is equal to simply replace whatever I have here with big X, right, big X over 2, right. As I told you, this will be some function of what is on here, what is here, right, the random variable on the right side of this thing. So, this is just x over 2 is your conditional expectation, it is a random variable. Okay. So, and if you wanted conditional expectation of x given y, you would do the same thing, you will find the marginal of y, right, find the conditional of x given y and integrate that, okay, you will get some other function of y. Okay. Okay, so, understood so far. So, in the discrete case, you find some expression in terms of whatever value you are conditioning on and blindly replace that small letter by a big letter, so that it becomes a random variable. Okay, that is as simple as that, this is almost mechanical, right. Okay, great. So, now you know how to, for the case of jointly continuous and discrete random variables, you know how to compute conditional expectation, which is a random variable, which is not a number. Yes.
So can we see the expectation as an average flow? What is the notion of expectation? Because here the expectation comes as a random variable.
Right.
But if we see it as a notion,
the conditional expectation is a random variable. Expectation is always a number.
But if we see expectation as an average phenomenon, it should come something finite or something which is deterministic.
Yeah. So the expectation will have the interpretation of the average, right. So that we will do much later towards the end of this course. Right? We have not got it. So far as you are concerned, expectation is simply a number, right. I have not given it any interpretation, it's just integral x dp, right. The interpretation of the expectation is given by the law of large numbers. Okay, we have not, I have deliberately kept it just like a number, right. I have not given it any interpretation, and conditional expectation is a random variable, that is all I have said so far.
So if we compare it with the average phenomenon, then psi of little y will be more appropriate.
No, I am looking at this, yeah. So this is, if you are given x is equal to little x, then you can view this as given x is equal to little x, what is my expected y, right. So that is what this is, but this little x itself changes values, right. I mean, what I mean is that this capital X can take different little x's. So if you then this becomes, then the conditional expectation, this conditional expectation is a random variable is what I am saying, and it changes value depending on what values this x takes. Okay. So properties, so I just move on to properties now that we have done this example. So again so you have this psi. So let us say psi of x is equal to expectation of y given x, right. So this is a random variable which is only a function of x or y. I mean it could be x given y, right, does not matter. Theorem, law of iterated expectation. So this is a very important result. It says that expected, so the psi x is a random variable, right. Now this, if I take the expectation of that random variable, I get, so this is well defined, right. So this is a sigma x measurable random variable. So if I just average over the distribution of x, I will get some number. So what happens is that you get the expectation of y, okay. It is a fairly remarkable important property of conditional expectations, okay. So so a more fancy way of writing it is, so it is called law of iterations because the more fancy way of writing it is expectation of y given x equal to expectation of y, right. So this is why it is called law of iterated expectation. You have two iterated expectations, right. So this is a little, it is a slightly less transparent to write it this way, right. So here the interpretation is you are taking expectation of y given x in that sense, right. It will be some random variable which is a function of what is on right side of the stick, which is x, and then this expectation is with respect to x, right. Sometimes you people write little x, so just big X here just to sort of make explicit the fact that you are taking expectation with respect to the distribution of x. It can't be anything else, by the way, right. So it's, this is a random variable which is a function of x, right. Y is already averaged out, so to speak. So if you do that, you get back the expectation of y, okay. So this is a fairly important deep property of conditional expectation. To proving it is, so I mean, so far we have only defined it for discrete and continuous random variables. So any proof we can supply will only work for discrete random variables and jointly continuous random variables, in which case we will just write out the expressions and just prove it, okay. Let us just do this for the discrete case, okay. I will do it for discrete, you do it for jointly continuous, and then we do not know anything beyond that at this point, right. What we can do, we do not know. So it is actually a fairly mechanical proof. So expectation of psi x, which is expectation of y given x, is nothing but sum over x p x of x times expectation of y given, correct. So psi of x is a random variable as a function of x, x itself takes a discrete set of values, right. So this is psi of little x, right. So this whole thing is psi of, correct, then it makes sense, right. Now what am I going to do? I am going to write that out, okay. So that is sum over p x of x, then I have sum over y times p x y given x, isn't it. So y given x of y given x, correct. So if you just do that summation, so y times you have that So, I can write this out, right. So, I have sum over x p x of x sum over y times joint over p x of x, okay. And then these will go, correct. So, then you will get sum over x comma y times correct, which is nothing but the expectation of y. Okay. So, I have been a little bit sloppy about not worrying about the order of summation and so on, right. So, if your random variables are all non negative, there is no problem, and also when the random variables all have well defined. So, if expected absolute x, expected absolute y are all well defined, you can interchange, there is no problem. Okay. I have been a little bit sloppy, but this is the essence of the proof. Okay. Okay. So, is that clear? So, actually intuitively this is not all that difficult to comprehend. I mean, at a very elementary level, you let us say you have a class which has, let us say, several sections, right. You are just computing the class average by averaging these separate classes and then taking weighted average based on the number of students in each class, right. That is roughly what you are doing, right. You can think of what you are conditioning on as the section, right. Inside that section you are calculating an average, right, and then you are calculating weighted average across the classes, right. That is roughly what is happening, right. So, and then it is not surprising that if you do that you should get the overall average, right. Similarly, you can prove it for the jointly continuous case, except all these summations will become integrals, correct. So, but this is an important result, law of iterated expectations. Expectation of y given x is equal to expectation of y. So, I will give you an application of this law of iterated expectation. Consider do you remember random sum of random variables you had. So, S n is equal to sum over I equals 1 through n x I, right. So, where x I let us say are x I is our IID and n and x I are independent, n and all the x I's are independent. Okay. So, in this case if you want to compute expectation of S n, okay, you can do the following. I can just write it as expectation of S n given n, correct. So, what is expectation of S n given n? So, I have to see in order to compute. So, this will be some function of the random variable capital N, right. So, first before I compute that I should compute fix n is equal to small n and compute, correct. So, let us compute consider expectation of S n given n is equal to n, okay. So, I am fixing n equal to n. So, I will get what will I get? I will get expectation of sum over I equals 1 through n. So, I will get this, right, x I given n is equal to little n, correct. So, this is equal to expectation of sum over I equals. So, I am conditioning on n equal to little n, right. So, I can put a little n here, x I given n is equal to little n. So, far okay. Now, I have to use the fact that n is independent of all the x i's. So, conditioning on n equal to n does not change the distribution of the x i's, and therefore, it does not change the expectation of the x i's, correct. So, this will simply become, you can remove the expectation is what I am conditioning, right. So, this will simply become right. So, on this we know, right, this is just n times expectation of x, because all these x i's have expectation of x as their mean. So, great. So, this we know, right, so far with me. So, expectation of, thus expectation of S n given n will be equal to blindly replace small n with capital N, right, n times expectation of x. So, what kind of an object is this? This has to be a random variable, right. This is the conditional expectation, this is a random variable, that is a function of n, this guy is just a number, expectation of x is just a number. Therefore, expectation of S n is equal to expectation of S n given n, which is nothing but expectation of n times expectation of x. Okay. So, if you are summing random variables, IID random variables such that the number of terms in the summation is also a random variable that is independent of the x i's, you get the expectation of the sum is essentially the product of the expectation of n and each x, which seems to make perfect sense, right, it is perfectly intuitive. So, as an aside, so I mentioned earlier, I think that there may be scenarios of interest where capital N is dependent on the x i's, right, such as gambling, right. You may stop, the number of times you gamble may depend on how many you won and how much you lost, right. In those cases you cannot apply this, right, but you can apply somewhat more sophisticated techniques of analysis, and in particular when n is what is known as a stopping rule, a similar in exactly same equation holds. Okay. So, I just wanted to mention that as an aside. So, even when n is dependent in a certain way on the x i's such that you stop gambling when you either lose $100 or win $100, let us say, even in that case this will hold, okay, but it is not following from our proof. Okay. So, such an n that depends on the previous x i's is called a stopping rule. Okay. We will not cover that in this course. So, basically in the case when n is dependent on x I, you can no longer make that step, because if you condition on n equal to n, the distribution of x i's will change, then you cannot go from there to here, right. So, you have to use some other techniques, but the similar equation holds. Okay. So, that equation is called Wald's equality. Okay. So, I want to state a generalization of this law of iterated expectations. More generally, we can show that for any measurable g with expected g of x finite, we can show that expected value of y minus psi y times wait a second. So, y minus psi x, I guess y minus psi x. So, y minus psi x times g of x equal to 0. Okay. So, in other words, or so what I mean is expected y g of x is equal to expected value of expectation of y given x times g of x. Okay. So, the psi of x is nothing but expectation of y given x. Okay. So, what we are saying is, so the earlier version is simply with g of x is equal to 1, right. The earlier iterated expectation is when g of x is equal to 1, right, expected y equal to expected y given x, right. Now, I am saying that no matter you can put any function of x you want and this will hold. Okay. Okay. So, this how will you show? You can actually write it out again, right. So, we only know, after all we only know this definition for the case of discrete random variables and jointly continuous random variables, just write both out and see that this works, right, whenever these expectations are defined, right. It is a very like that, just write it out. So, this you will be able to prove, right. So, I do not want to waste time proving this now, because I want to give a very nice geometric interpretation to this. Okay. So, what this is saying, so now okay, so now it is useful for us to think of expectation of y given x as some kind of an estimate of y given x. Okay. So, you think of x and y as two random variables, dependent random variables in general. So, generally if I give you x, you know something about y, right, if they are dependent. So, if I only give you x, let us say I only give you humidity today, x is humidity let us say, and y is some temperature or something. So, if I give you humidity, you may be able to give some estimate of the temperature in some sense, right. So, that is the kind of scenario we are looking at, right. So, y you do not know, x you know. Okay. So, you can think of expected y given x as some estimator for y that only depends on x, because x is known to me, right, only based on x I am estimating y, right. So, what this is saying, what our equation is saying is that so another way of looking at it is that y minus the estimate of y. So, this is nothing but expectation of y given x, right, this is psi of x, y minus estimate of y, right, which is the error in estimate, so to speak, right. So, y minus expectation of x is the error in your estimate, is uncorrelated with any function of x. Okay. Okay. So, covariance between this random variable and that will be 0, right. So, if you want to interpret this geometrically, you can say that the error is orthogonal to any function of x. Okay. So, if you are living on, so let us say these are all L2 random variables, right, finite variance random variables. So, you are living on, so this is, I am just drawing it like some Euclidean space, but this is really some Hilbert space, okay. And you are looking for an estimate of y, or estimate of y, right. So, you are, so let us say this is my, let us for the sake of argument let us say this is my y, I want to estimate y, okay. And you are constrained to the subspace. So, you are given x, right, so you any estimate you want to make has to be a sigma x measurable random variable, right, it must be measurable with respect to sigma x, right, the set of all events determined by realization of x. So, the sigma x measurable random variables form a subspace of this Hilbert space that you can show, okay. And what you are saying is that, so if this is your y, okay, and g of x is any random variable in this subspace, all right, and what you are saying is that your estimation error, after all this psi of x is a function of x, all right. So, psi of x is somewhere here, okay, and you are saying that the difference between y and the estimate is orthogonal to anything here, any vector on this, right, which means that your in some geometric sense your conditional expectation is the foot of the perpendicular from y on the subspace of sigma x measurable random variables, okay. Now, do not ask me what these axes are, right, this I am just, this is some Hilbert space, I am just drawing it like some R2 for your easy picturization, okay, fine. So, y minus expectation of y given x, which is that vector, which is the estimation error, is orthogonal to the space of sigma x measurable random variables, okay, that is what this result is saying. Which brings me to the point of defining this conditional expectation in full generality, okay. So, the conditional expectation in full generality is defined using this equation. So, for any function g of x, measurable function g of x, there exists a unique sigma x measurable random variable which satisfies this equation, such a psi x is called the conditional expectation, okay. So, that psi x can be shown to exist uniquely up to almost surely unique, okay, and it has its orthogonal, I mean it has that interpretation, it is basically defined as the foot of the perpendicular on the space of sigma x measurable random variables, okay. Okay, great. So far okay. So, this is what is used as the defining property of conditional expectation when x and y are not necessarily discrete or jointly continuous or any such thing, they can be whatever they want, and Kolmogorov proved that such a random variable psi x exists almost surely unique, okay. So, that is taken as the conditional expectation, okay, but it cannot be given as a explicit formula, some random variable exists you can show. Now, that brings me to another geometric point. I said that this is your estimate, right. So, I said this estimate is your best estimate of y given x, and it is your estimate lying in the space of sigma x measurable random variables, correct. Now, we can show that expectation of y given x is in some sense the best estimator, okay, in the squared error sense, okay. So, if you have any function whatsoever, some h of x, so h of x is some sigma x measurable random variable, you can show that its error from y will always be bigger than or equal to the error from your conditional expectation, and geometrically it makes perfect sense, right. So, suppose you are given a point y outside the subspace, you want to find a point in the subspace which is closest to your y, you would just find the foot of the perpendicular, right, in Euclidean space, and the same intuition goes through even in this Hilbert space, this is all some Hilbert space of L2 random variables, right. So, this theorem the conditional expectation is conditional expectation E y given x is the minimum mean squared error or MMSE estimator of y given x, and minimum mean square estimator of y, okay. I.e. for any measurable h, we have expected x minus, well I should say, okay, I think I am going to mix it up a little bit now. So, y, so I am y, so this is what I want to say, y minus expectation of y given x the whole squared is less than or equal to the expectation of y minus h of x the whole square, okay. So, y minus h of x whole square is that norm, right. You know that this behaves like a norm, right, expected square expected or the squared norm rather. So, this is less than or equal to that is what we are saying, okay. So, okay, is that clear? Okay, I think I have to stop here because I am out of time. Yeah, maybe we will continue with the proof of this next class and move on to the next topic. It is actually a fairly straightforward proof.